Okay, so the next class of biological molecules that we're going to be talking about is lipids. All right, and lipids is actually a broad class. It's comprised mainly of two types. There are what are called triglycerides, and there are steroids. All right, most lipids are going to be the triglyceride type. The thing that makes both triglycerides and steroids, what they have in common is that they both tend to have very low aqueous solubility, but they would have very good solubility in nonpolar solvents. All right, and when I say nonpolar solvent, it would be something like hexane, which is chemically similar to gasoline. All right, it would actually be easier for human fat to dissolve in that than it would be for it to dissolve in water. And you probably have some sense of that if you've ever seen tried to clean out a pan that's had bacon fat in it. All right, water tends to not like that fat, but there are some solvents that would dissolve that. All right, so first of all, let's start with fats and oils. All right. All right, and so by fats and oils, what we really mean is this type of molecule called a triglyceride. All right, sometimes it's also called a triacyl glyceride, but a lot of times people just generically refer to these as fat. All right, so the type of molecule that you're going to have here is always the same in general, but there can be small differences. All right, and so it always is going to, so this is what the fat molecule looks like, but it's comprised of what's considered glycerol plus 3 fatty acids. All right, so if I took this fat molecule right here and I broke it all apart, all right, this part of it right here, hopefully you can see, would be this molecule right here. That is glycerol. All right, it's also the same thing as glycerin. But this part attached to that glycerol, you'll notice that you've got 3 esters on it. All right, so this right here, that's an ester bond, that's an ester bond, that's an ester bond. And so all 3 of these parts right here are what are considered the fatty acid part of the triacylglyceride. All right, so these right here would represent 3 what we would call free fatty acids. All right, and if you ever hear the term free fatty acid, that's to distinguish the fatty acid when it is in its carboxylic acid form, when it's not linked to a glycerol molecule, versus this type of a fatty acid. People would say that this right here is a fatty acid. All right, it's not really a fatty acid. It's a fatty acid that has been joined to a glycerol molecule through an ester bond. All right, so you would not say that these 3 things right here are free fatty acids because they're connected to the glycerol molecule. All right, so the way the fat molecules can be synthesized is if you take glycerol and you take 3 fatty acids and you heat this with a little bit of an acid catalyst, and it's going to undergo what's called an esterification reaction. All right, and this is we mentioned with the proteins that some certain types of reactions are considered condensation reactions. This is another example of a condensation reaction, because if you look at what was there between the carboxylic acid and the alcohol, well, there are some atoms that are no longer there when they're joined together as the ester. All right, you'll notice that this OH right here is missing, and you've got a hydrogen from the alcohol that's missing. So again, that's H2O. All right, and that's why when I've shown this reaction right here, we have 3 water molecules as a byproduct. So triglycerides can be broken down into what we call fats and what we call oils. All right, and they're pretty similar. The big difference between a fat and an oil is just simply what state of matter it is at room temperature. If it's solid, we tend to call it a fat. If it's liquid at room temperature, we consider it an oil. All right, so the question is, what is the chemical difference between a fat and an oil? What makes something want to be solid at room temperature versus wanting to be liquid? All right, so when you have a fat, all right, essentially the fatty acids that are going to be involved are what are considered saturated fats. Or more precisely, they will have saturated fatty acids, which are esterified to the glycerol molecule. All right, so I've done a little shorthand when showing this. So when I show this little squiggle, you can just assume that there's, a long chain hydrocarbon, just like here. All right, so what it means to have a saturated fatty acid is that it's just going to be a hydrocarbon chain with all single bonds. All right, and the reason you call it saturated is this thing right here is this carbon chain is holding as much hydrogen atoms, or as many hydrogen atoms, as it possibly can. All right. By comparison, an unsaturated fatty acid is going to be one that has double bonds in it, like I'm showing over here. All right. And so this thing right here is not holding as many hydrogen atoms as it could, because if we take this from a double bond and turn it into a single bond, you can add a hydrogen to each of these atoms. All right. So the thing is, when you have these triglycerides, where these esterified fatty acids are saturated, what ends up happening is you get these things can stack together very efficiently. All right, so this is one fat molecule right next to its neighbor over here, and you can see that these parts of the molecule, the hydrocarbon chain, they can stack to next to each other really efficiently, and that creates a very efficient London dispersion force interaction between these. All right, so remember, London dispersion forces are the type of intermolecular forces that can happen between any molecules, and it's the reason that once a molecule gets large enough, they tend to want to stick to each other. All right, but this particular force is much more efficient if you've got a large straight surface for two neighboring things to pack together with. So because of this relatively efficient attraction between these tend to be solids at room temperature. All right. When I say that it's a relatively strong attraction, keep in mind, by comparison to like hydrogen bonding, this is actually very weak. All right, so weak that even though these are solids at room temperature, if you've ever tried melting butter, you would realize that you don't need much heat in order to get rid of this interaction right here, or to overcome that interaction. All right, so by comparison, oils tend to be triglycerides where the fatty acids that are esterified to the glycerol tend to be unsaturated. All right, and so that means that they're going to have some double bonds along their length. By the way, the actual fatty acids tend to be between 16 to 18 carbons long. I've tried to draw a long chain here, but the actual lengths would probably be a little bit longer for actual fatty acids. All right, so what does having these double bonds do for the chemistry? All right, well, what ends up happening is that as you should know, whenever you have a double bond, it locks in that particular molecular geometry. All right, you've got a 120 degree bond there, you've got a 120 degree bond right here, and there is no free rotation around that double bond. All right, so essentially the way it's described is that puts some kinks in that chain, and it makes it so that this hydrocarbon chain right here doesn't pack against this neighbor nearly as efficiently as when these are totally saturated. All right, and because they don't pack together as well, the London dispersion forces that you would have between them is not as significant. All right, therefore these things tend to be liquids at room temperature. All right, so chemically that's going to be the difference between oils and fats. All right, but if you take a look at the molecule as a whole, you still have, it's still a triacyl glyceride. All right. So one property about triglycerides is that even though they're relatively stable, they can go bad. All right. So one way that we know that triglycerides are relatively stable is that we have several of them. You probably have several of them in your kitchen that are stored at room temperature. All right. So if you have vegetable oil, that's going to be a triacylglyceride, and because you can store it at room temperature without it going bad, that's an indication that it's relatively stable. But there are some ways for the oils to go bad, and when they go bad, it's considered going rancid. All right, so when they say it's rancid, it's going to have a bad odor. Maybe its color might change a little bit. But there's two types of rancidity that you can have. One is hydrolytic, and the other is oxidative. All right, so hydrolytic rancidity occurs whenever the triglyceride undergoes a reaction with water. All right, so if you recall, if we were to try to make a triglyceride, you get this esterification reaction, and you call it an esterification because you're making an ester. All right, remember that we spit out water molecules as a byproduct. All right, so if we wanted this reaction to go in reverse, we would need to add water. All right, so whenever you have hydrolytic rancidity, all right, the reason they call it hydrolytic is the hydro part means water and the lytic means breaking apart. All right, so you're literally breaking a bond using water. All right, so in this case, you would be breaking the ester functional group apart. All right, and if you'll notice that when that happens, you now have an extra H here and an extra OH here that weren't part of the ester. All right, so that's where that water molecule went. All right, so when you get this, if that were to happen to only one of your esterified fatty acids, that would make what you would call a diglyceride. All right, because it's only got two esterified fatty acids to it. All right. This one right here would now be considered a free fatty acid. All right. So the thing is that, and one other thing, you could imagine this diglyceride being reacted with water, and you could clip this one of these fatty acids off, and that would leave you with a monoglyceride. All right. But the thing is, whenever you have the either the free fatty acids or the glycerol molecules, these are going to be they're going to give off a little bit of an odor, and if that were to happen, you would say that oil had gone rancid. All right. So another type of rancidity is oxidative rancidity. All right. And so oxidative rancidity always involves oxygen being added to the double bond of one of the fatty acid chains. All right. So you're not responsible for knowing the exact mechanism of this, but some form of oxygen, could be oxygen in the air, could be water, is going to react with this double bond to introduce some type of oxygen. All right. So, and from the previous unit, you probably know that once you get an alcohol, that alcohol could get oxidized up to a ketone. But any of these forms are going to be a little bit less stable than when it is when it has not been oxidized.